Okay, I guess you can hear me clearly, no noise.
Yes, I can hear clearly.
Okay, so we're going to see some important rules about derivatives. How you can apply the derivative as an operator to functions when you're taking the product of the function or quotients, and some trigonometric stuff. So these.
Yes.
Gone?
Yeah, I'm back. Sorry.
Oh, you're back. Let's see. Let me just um okay, I don't know. So yeah, so there was some issue with the stream. Okay. So he talks about formulas of differentiation derivatives. He says there are specific examples of these cases when you have specific functions, and there are other examples where they're kind of like, you can think of like algebraic identities that work for any function. So yeah. By the way, they use this convention for u plus v of x equals to u of x plus v of x, and uv of x is equal to this. Does anyone know like what kind of function behaves in this manner? Any idea about?
Can you please repeat once again the question?
Yeah, I'm asking like what kind of function behaves in such a manner, like where you have when you add the two functions
I
and you.
think this rule applies.
Sorry?
I think this rule applies only for continuous functions.
Right, right. And why do you think it is needed that they have to be continuous?
If for some point they are not defined, then after combining them, some problem will arise, I think. But
Yeah, that's basically it. And there are other kinds of functions which look like this, but not exactly. They're called linear functions. So in linear functions, you can add them, and they will behave in this manner. So yeah. Okay. So he's trying to prove this thing, so that u plus v is equal to, I guess this is a typo, but this is u plus v prime is equal to u prime plus v prime. So we're taking the derivative. And the way to prove it is basically simple. You just use the expression we had before of derivatives in terms of limits, right? Instead of f, you just replace u plus v, and you get this, right? Because your function is a summation of two functions. So that's that, and you apply this thing here, and you simplify it a bit. What you're going to get, you're going to get the limit of two things that look exactly like the derivatives, right? So these happen to be your derivatives. Thus u plus v prime happens to be u prime plus v prime. And you can do the
Yeah,
same.
makes sense.
Yeah, you can do the same for multiplication of a constant.
Sorry, if you can do this with a constant?
Yeah, I'm just said you can apply the same technique of having limits, writing them in terms of limits, and just having this constant multiplied to the function, and you'll get this thing. Basically, so that's pretty much the first thing you have to remember, that when you're taking the derivative of two functions that are being added, you'll take the derivative of each function separately and then add them. And if you have a constant multiplied to the function, you can always pull the constant out of the function, then take the derivative and then multiply. So
Yes, so we take the constant common and then just
no, it's not.
limit.
It's not common. That's not the right way to think about it. Mostly, what you have to think is that derivative is an operator, right? And this operator cares only about functions. It does not care about constants. So what happens is that when you take the derivative of a constant, it is the same thing as a constant. So it gets multiplied. So it's not that you take it common, but it's kind of like the operator does nothing to a constant.
No, I mean such as to prove that cu dash is equal to cu multiplied by the derivative of u.
Right.
So I took the limit as delta x approaches 0 of the cu x plus delta x minus cu into cu of x
Right.
upon delta x. Then I took the constant outside common. Then I took the limit. So I got the
Yeah,
u dash.
okay, basically that. Yeah, that you're right. Yes.
So I got u dash. U dash. So c into u dash is equal to the derivative of cu dash.
Yeah, that's correct. So yeah. Now we try to evaluate derivatives of the trigonometric functions. Let's see. So we saw this thing, sine x over x, how it approaches 1, and 1 minus cosine x over x, how that also approaches 0. Now if you try to take the derivative of sine of x, evaluate it at x equals to 0. So this notation again is this notation of x as a subscript means at what value of x you're evaluating the function, right? So here the function sine x is being evaluated at x equals to 0, so you put in x equals to 0. So this is again same thing, you write it in terms of limits. You turn out to be sine delta x minus sine 0. Sine 0 is 1, so this is sine delta x over delta x. So you can see how we used the limit of sine x over x to evaluate the derivative of sine x, right? And
What's exactly the difference between taking the limit x to 0 or evaluating it at 0? What's the difference?
The difference is that it's the same thing, but limit is kind of like how the function behaves when it approaches, but it's not exactly as just putting in the value. Because again, if you put x equals to 0 here, sine x over x, you're not going to get 1.
Yeah, so it just means plugging. It doesn't mean plugging in 0, right? Also,
Right.
because it's not possible.
Yes.
Okay. Sure. Okay.
So
I
yeah,
think
go on.
I think this proof is just for x equal to 0. Then I think the general proof is given later.
Yep. This is just for sine x when x is 0. Yeah.
And this is assumed leaving the above limit true.
Yep.
Sin x by x equal to 1. We are just assuming it is true. And the other proof doesn't use that.
Right. Yeah. We evaluated it, so they're just computing it from what we evaluated earlier. Yeah, and they do the same for d by dx of cosine x evaluated at 0. They use this thing cosine x minus 1 over delta x 0. So that's 0. So what the goal with doing this is that if you can evaluate the derivative of this function at x equals to 0, you get some kind of idea about how it will be like. Right? Now for any arbitrary x, what you do is you write down the limit expression of the derivative. So the limit of sine of x plus delta x minus sine of x over delta x as delta x approaches 0. You apply the identity of trigonometry, trigonometric function sine a plus b is equal to sine a cosine b cosine a. So you expand it out. Your sine x gets cancelled. Sorry, your fraction gets divided. You have sine x cosine delta x minus 1. So you take sine x common, right? You'll be left with delta x in the bottom, and here you'll have cosine x, sine delta x over delta x. You use the previous arguments we had about so actually this also assumes that
Limits to be true.
right, yeah.
The 1
So
minus cos x.
yeah, so this goes to 0, this goes to 1. So you're left with d by dx of sine x is equal to cosine x, because this term blows up because this is 0. So you're left with just cosine x. So that's the thing. The derivative of sine of an angle is the cosine of that angle. And you do the same for the cosine function. You're going to use cosine of a plus b and other identities related to cosine, and you'll reach minus of sine x. Can be a good exercise if you're interested. Okay. Not sure if they're going to use no, they don't. If you try to figure out how the derivative of this sine, this cosine, geometrically without using any notion of limit, you'll have to resort to pure trigonometry, and it can be fun. It can also be very useful, but yeah, they're not doing that here. You can try that.
You mean the picture where he draws a circle? Is that what you mean? The geometric proof?
I'm kind of meaning to say like sine function as the sine wave, and you try to see when you take the derivative, the graph changes. You'll get the cosine x wave.
Oh, okay, the wave. Okay, so, sure. Okay.
That can be interesting to see how the derivative applies to that. And it is not really that difficult. You just see how the graph shifts the wave. But yes, let's see. So product formula. The product formula is another important thing that you'll use all the time. So it just says that taking the derivative when you're multiplying two functions is equal to taking the derivative of the first function, then multiplying with the second one, plus taking the derivative of the second function, multiplying with the first one. This is actually, so some people wonder why, like, if you try to think about why someone would come up with this formula. Like, okay, we can prove it for sure, but why would someone even think of the derivative acting like this, right? And the answer you're not going to get now, but it turns out the derivative operator is a special case of a very general structure of operators, and they act in this manner. So for example, if I give you a very short look on what it will look like, so derivation, yep, you see this? Of course, you're not going to understand the words and whatnot.
I'm still amazed by how structured you are, how organized. Jesus.
Yeah, so this is a derivation. So this is exactly what you're going to learn, what we learned in derivatives in the calculus course, but this is a very abstract thing, right? So it acts upon something called an algebra, so that's an algebraic object, you can think of it as. But a derivation is a linear map, so it's a linear function which satisfies this rule, right? So this is your exact product rule that you saw. You see, d of v multiplied w is d of v. So this is d of v just means v prime times w plus v times w prime. So this is why the product rule that we saw looks like what it is. You know, it's not that someone just came up with it and then it works. It's part of a bigger picture.
Okay. What was the dot again? The big dot?
The big dot, you can think of it as just multiplying two things in a set. Yeah.
Oh, okay, sure.
So it's not going to make sense. I agree. So algebra here is kind of an object. You can think of it as like a set with some things you can do with the set. For example, you can add elements to the set, you can multiply, and you can do other things. So this A can, sorry
to interrupt. By the way, what do we mean by an algebra?
You're not going to understand that right now, but an algebra is an algebraic object. That's what I can say. Like set. It is like it's hard to give an intuition about it. Do you know about groups? Anything like that?
No, I have
Okay.
not been introduced.
Okay, yeah. So an algebra is basically, as you can see here, it's a set with some operations on it. So algebra A has operation addition, looks like addition, or this is scalar multiplication. So this is just this small dot is for multiplying with constant. This big dot is for multiplying with other elements in A. So like this set A with all these things with it and satisfying some properties is called an algebra. So it is like that. Example of algebras, it's difficult to give, but you can think of it like having the real numbers with addition, multiplication, and dot product in them, right? So yeah.
So algebra we can define as something, some group, not the mathematical group which I don't know, but some type of system in which some operators are defined.
Right. It's a structure. Right?
Where some operators are defined and we can perform them.
Yeah. So this is like a very abstract notion of some things that we just take for granted when we learn things. For example, number system, the natural numbers. What is natural numbers? Well, natural numbers is a set of things where we are allowed to multiply things, and we're allowed to have an identity called 1. We're allowed to have something called 0. So when you abstract things out, you're going to see that we don't care about numbers anymore. So for example, this is one of the things that when you go more abstract into math, you just forget numbers. You don't care about numbers. You care about these abstract things and symbols. But yeah, so I introduced this just to show that the product rule is not just something out of the universe. It is something that satisfies this, and it is called Leibniz rule because Leibniz was the guy who came up with the product rule in calculus, and then it was abstracted out. So that's the mathematical intuition, not intuition, like motivation for what the product rule is. Also, hello, Nobita. So continuing, we're going to see how to prove the product formula. Also, hello, Hojie, you're back.
Yep, back home.
Yeah, we were just getting into product rule.
Cool. Yeah, I joined when you were starting to talk about algebra, and I was like, wow, that's really advanced and cool.
Right. Yeah, I just thought it would be like interesting to show that product rule is not just something you have out of the universe. It's the same for determinants, by the way. Some people believe that the Cramer's rule is like the golden rule of determinants, and it came out of nowhere. But the thing is, determinants with the Cramer's rule is like the most stupidest thing ever. When you realize determinants are something else, you forget Cramer's rule. But yeah, that's kind of like those kind of things you learn, but you have to realize it is part of something very big.
Is the determinant type rule which we are talking as Cramer's rule?
Yeah, it's like multiplying, cross multiplication and subtraction, the Cramer's rule.
Oh yeah, I never do that. Well, I just use like code to just determine the determinant.
That's the thing. That's why it's useless. There's nothing to learn in Cramer's rule. You just know that it works like this, and you give it into a computer, and it works it out. But why do we care about determinants then? Yeah, let's get back to the notes. So what you're going to do is you're going to evaluate the two sides separately, and then you're going to show that they're the same. That's basically that. So you first evaluate uv prime. So uv prime is going to be you just replace f with uv in that limit expression we had earlier, and you get this. You simplify it a bit with the previous condition we had of functions multiplying. So uv of x plus delta x becomes u of x plus delta x times v of x plus delta x. So you have this. Right. So what they do is kind of like a manipulation trick in algebra. They add this thing to the numerator, right? So this thing is just basically u of x plus delta x v of x minus u of x plus delta x v of x, which is 0. If you add that, you're going to get some nice thing actually. So you have this plus this. So now what you can do is you can take v of x common and a few other things common, and you'll get you'll get this. I mean, this is just a trick to manipulate and get to the point we want to get.
Right.
Yeah. So this is u of x plus delta x minus u of x over delta x times v of x, taking v of x common. Same here. What this leads us to, well, this is basically u prime, and this is basically v prime. So you're left with u prime v of x plus u of x v prime of x, right? So that's basically it. There's nothing in there. But what is more interesting is like if you think about it, like let me just ask, how do you think about like multiplication of functions? What does it mean? What does it mean to multiply two functions?
Taking the outcome and yeah, it's a multiplication of outcomes. Is that
No, I mean if
something
I
you
have
want?
like f of x and g of x as two functions, so what does it mean to have f times g? Like what does that give me? Like what is that new function in terms of the other two functions?
I think when we multiply the functions, we just get a new function, which
That's
is
the
just
thing.
equal.
But how is the new function related to the other two functions?
I mean, when we put a value of x in the new function, suppose we have function fx and gx, and we multiply to get a function fg.
Right.
Fg, and we put some value x in fg, then the value of fgx would be equal to fx into gx, which means the value we put in x, f and x, put in the product.
Right. So the product of two functions just means that every time you apply the product to something, some x, you have to take separately how that x gives you in f and g, and then multiply them to get something in fg, right? So that's basically that. But the thing is, it's kind of easy to confuse it with the composition of two functions, which is entirely something different. But yeah, that's the product. Okay, so they give an intuitive and graphical proof of the product proof, which is very interesting. Is I don't know. To me, it's not as interesting because like every book has exactly this kind of proof. But for someone starting, it has to be interesting because the algebraic proof is basically manipulation. So what we're doing, we have v and we have u. We increase v a bit. We have delta v as its increment and delta u as its increment. So you have that. Now what you're trying to do, the goal is to show like the area. Let's consider this. So the area covered by v and u. So this orange rectangle, now this is your area, is equal to so right. So yeah, so the goal is to find out the area of the largest rectangle, the bigger rectangle, in terms of v and u, basically. So let's see. The inner rectangle has area uv, obviously. Delta u is u of x plus delta x minus u of x. That's how you define the change in a function, right? Then you do the same for v actually. So what they're doing is that u of x plus delta x is equal to u plus delta u. Yeah, v of x plus delta x is equal to v plus delta v. So the area of the big triangle, sorry, big rectangle is u plus delta u times v plus delta v. Makes sense. If you let v increase and keep u constant, so if you let kind of like you restrict u from going against this boundary, so you just increase v, you'll get this. And if you stop increasing v and you increase just u, you're going to get this, right?
Gotcha. This is a little bit odd geometric proof because it feels like it's making it approximation because we need to ignore the smallest rectangle delta u times delta v.
Right.
But yeah, it's like we're trying to find the difference between the large rectangle and the small rectangle, and that's approximately like the red area and the orange area on the side, like flanking. Yeah, and we just ignore the small one because they're supposed to be you're multiplying two small quantities.
I see. Yeah. That's basically. So here delta is. Sorry.
I think we just ignore them due to them being of the second order.
Yeah. You can think of it as like ignoring the second order as well. Yeah, that's a good point.
In calculus mid-degree, this was defined as something in terms of orders. The smaller than they multiply.
Right. Yeah.
And it is quite convenient to ignore them.
Yeah, I think I would think of these deltas as infinitesimals. What you try to do integrals, kind of like a very, very infinitesimal increment, which, if it's small enough, can be just approximated to 0. So the thing is, this white rectangle, just left out, whatever it is, if your delta u and delta v are small enough, you can just ignore this part, right? So thus the whole area happens to be u delta v plus v delta u, as you would expect, according to the product rule, right? And when your delta x goes to 0, you're just going to get the derivatives. So that's another thing. Actually, I believe they're going to introduce it later, but one has to be careful when talking about infinitesimals and how the limit takes them to derivatives. Sometimes it's not as trivial. Okay, so we have the last thing, the quotient formula, the quotient rule. So when you have the derivative of two functions being divided, so like what would the derivative of them look like? This is also like product rule, not something out of nowhere. It has a name. It's called the Jacobian identity. Something like that. I'm probably misnaming it. But yeah, it's something like the Leibniz rule I showed you. What you're trying to do is find the derivative of u over v. So you have u of x plus delta x over v of x plus delta x minus u of x v of x, right? Which is just this in terms of notation. You evaluate the subtraction of fractions. You get this. You take things common, and uv and vu gets cancelled. Yeah. So you reach here, which is delta uv minus u delta v over v plus delta v. So what you now do is so if you multiply 1 over delta x to the both sides of the equation, what you're going to get is this. So 1 over delta x times this is equal to delta u over delta x. So this is done in order to change these delta u, delta v's into derivatives. So if you have delta u over delta x, when you take the limit, they're going to go to the derivatives, right? So you have delta u over delta x, v minus u of delta v over delta x. The denominator stays the same. You take the limit. When you take the limit, you're going to get du dx minus u of dv dx, and the denominator becomes, of course, v squared. Delta x approaches 0. So this is your quotient rule: u prime v minus u v prime over v squared. And well, most of the time you don't have to remember the proof, but as an exercise, when I first learned it, I tried to just kind of like play around with it to get used to the proof. But yeah, most of the time you'll just need this expression to evaluate stuff. So
yeah, I haven't looked at the exam yet, but what can we expect a bit? We don't have to learn the proofs. What I can
no,
right?
You don't have to learn the proofs. The exams are going to be mostly an easier version of the PSATs. The PSATs are the hardest thing in the course.
Okay.
And as you can see, nothing in the PSAT is actually proof. It's more like computing and finding things out. But we can actually take a look at the exam.
Isn't that cheating?
No,
if you know the questions, then
because you're not going to have that exam. I'm going to change the paper, so yeah. That's pretty much what we did last time. Give me a second. Hello, Nobita. Browser sometimes sucks. 1801. Yeah, in the exam, you're not going to actually get the papers that is in the syllabus. Rather, I'll either pick up papers from past year exams, like from 1990s or something like that. The syllabus is same enough, or I'll just pick problems from other sources like books and whatnot. So.
Wait, sorry. This is not going to be the exam, the ones we are seeing right now?
Yeah, what I'm saying is the exam that is in the course will not be the exam that you will be preparing for or giving. So. Yeah.
Okay, so we can just use this as practices.
Yep.
Practice.
Yep.
Okay, cool.
The exam, it looks like this, basically finding things out or drawing graphs. Probably later in the course you will have to do more of these kind of things, like deriving stuff. But other than that, it's like this. You're going to... This has 7 problems, so I'll probably stick to 7 problems within how many hours?
Okay, sweet.
Let me see. each problem. They don't say it, but it's probably, we're going to do it probably like 1.5 hours. Something like that.
And it's gonna be on
No, okay.
Saturday, right?
It will be
Oh, sorry.
50-minute exams, okay. Sorry, what you were saying?
It's gonna be on Saturdays, right?
Yeah, it's going to be on Saturdays. It depends on how when we finish lecture 6, right? Lecture 6 would be finished on 2 Sundays after today, and then on that Monday we'll do lecture 7, which is reviewing the first 6 lectures, and then it will be on Saturday.
Okay.
Okay, so that was that. You have Quotient Rule, and I would encourage practicing problems from the book that's been given or from other places. The book that they're following, I believe I gave you, was the Analytic Calculus with Analytic Geometry, Simon's.
Simon.
Yeah.
And from which part should I practice? I'm a little bit confused.
Let's see. Okay, so this is your book. Probably, let's see. I mean, wait, they had the readings section, right? Yeah. So if you go to the reading section.
Yeah, in lecture 3 it says chapter 3.1, 3.2, and 3.4.
Yeah.
Yeah. So I think there is like a question for each section, so there might be questions for 3.1, 3.2, 3.4. So.
Yep, check the readings page. You'll see which things you'd have to see for what stuff in the chapter. They should have like some other like book as a reference, but they probably don't. But also, wait, I don't think 1801 has that, but 1802 had like what is called supplementary lecture notes, which are very nice. Also for the course reader, supplementary notes, exercises. Okay, these are the what is it?
So the ones which I should see now are which I can see, right?
Sorry?
The ones which I should refer now are graphing function and continuity.
Yeah, these are the what is it? The supplementary notes, which can help you with like knowing more about specific concepts. So, for example, if we open the approximation supplementary, that will look something like this. Yeah, so this is directly from a book, I believe, but with this supplementary stuff, you can go into deep about what they don't teach in the lectures. So the approximation here looks pretty nice. Yeah, it has physics examples, quadratic approximation. Yeah. I'm not sure, but if people are interested, what we can do is for each lecture, if we have something as the supplementary, we can go through it, because the lecture itself takes around like 30 to 40 minutes to complete, so we can spend some time else in the
Is
supplementary.
it true?
So what?
Is it true that sin x is approximate to x?
Yep, when x,
Just
when x is
as
small enough.
I saw when you were scrolling.
Yeah, like it's related to the Taylor expansion. If you write the Taylor expansion of sine of x, the first term is x. So if x is small enough, everything else disappears in the expansion. You're left with x. We're going to do that
If x
in.
is small,
Sorry.
if x is quite small, then the other terms will just decrease the value as the factors are increasing. So we can ignore that.
They'll disappear. Yeah. We're going to do that at the end of the course when we do Taylor series. I remember him saying that in the lectures. So we'll see that. Yeah, sine of x approximately is equal to x. It is like very much useful in physics when you're doing stuff with sine. So probably we can go through some of these supplementary stuff when we can.
Sounds good.
Yeah. And so I'll post PSET 1.1 later today in a few hours, and it's going to be due on coming Saturday, and we'll discuss that on Saturday. So,
Yeah.
okay. So yeah, thanks for joining everyone, and we'll see you on Saturday. Also, just to ask, Nobita, are you interested in showing up for this course? I'm just seeing you for the second time. If you're interested, you can do that. Yeah. Not sure if they're AFK.
It seems he's away.
Yeah, probably. Anyways, so yeah, have a great day, and we'll see you coming Saturday.